A simple calorimeter can be constructed by using two nested polystyrene cups with a lid, a stirrer, a thermometer, and a known volume of water to complete the setup. Calorimetry works thanks to the first and second laws of thermodynamics, that the energy in the universe is constant. It can neither be created nor destroyed, and thermal energy moves from warmer objects to cooler objects until their temperatures become the same. Therefore, enthalpy change can be based on thermal energy transfer in the calorimeter. The chemical reactions taking place here are typically facilitated by the aqueous environment. Combustion reactions, however, would be unsuitable in a simple calorimeter. However, in Chemistry 30, we make the assumption that the chemical mixture will still have the same density and specific heat capacity of water, and so needs to be fairly dilute. We also assume that there is no exchange of thermal energy between the simple calorimeter and the outside. Even the heat absorptive properties of the thermometer itself and the stirring rod will be ignored. And we assume the reaction takes place under constant pressure. So with these assumptions in place, as with any other calorimeter, we can derive a broad equation. That the energy or heat lost by the chemical reaction is gained by the water. The other way works too. The heat lost from the water will be equal to the energy gained by the reaction. So in summary, when taking place inside a calorimeter, the energy lost in a chemical reaction is gained by the water in the calorimeter or vice versa. And we assume the enthalpy change of the chemical reaction is exactly equal to the change in kinetic energy of the water in the calorimeter. Recalling that the change in kinetic energy of water, say, is mc delta T, and that the enthalpy change of the chemical reaction occurring in the water will equal the energy thus applied to the water, then the change in enthalpy of the chemical reaction will equal mc delta T. Here's a problem that will enable us to tie in a couple of the concepts we've learned so far. A 50 milliliter solution of 0.5 mole per liter hydrochloric acid is mixed with a 75.0 milliliter solution containing excess sodium hydroxide. In a simple calorimeter, the initial temperature of both solutions was 23.5 degrees Celsius. During this neutralization reaction, the highest temperature of the mixture recorded was 26.7 degrees Celsius. Determine the enthalpy change of the reaction and write a thermochemical equation. Now we can see from the information given that it is a heat lost, heat gained question. Energy is being lost in the neutralization reaction and absorbed by the water, causing the temperature of the water to increase. It is therefore an exothermic reaction. The change in enthalpy of the neutralization reaction will be equal to the change in kinetic energy of the water. The two formula we're going to be dealing with here are the change in enthalpy formula, since we're considering energy produced by the reaction, and the kinetic energy formula because we're considering a resulting change in temperature of the water. We will also say that the chemical potential energy lost from the system is equal to the heat energy gained by the water. So to determine the energy lost from the system, we shall calculate the energy gained by the water. The mass of the water is determined by the combining of a 50 milliliter solution and a 75 milliliter solution to form 125 milliliters of the reaction mixture. Since we assume these mixtures share the properties of pure water, they have a density of 1 gram per milliliter. Therefore, 125 milliliters translates to 125 grams. We use the specific heat capacity of water found in your data book. And to calculate delta T, subtract the initial temperature from the final temperature. Now, contraindicatory though it may sound, a negative value means the temperature has gone up. This will ultimately yield a negative energy value, meaning the chemical reaction is exothermic, as it would need to be if it increased the temperature of the water. The amount of energy gained by the water, and thus the enthalpy change of the reaction, is 1,676 joules. Since we conventionally express enthalpy changes in kilojoules, convert your answer accordingly, and the correct sign, and round to appropriate number of significant digits. I can't put this enthalpy change value directly into the chemical equation. In the equation, the energy value added to the product side refers to the amount of energy produced by 1 mole of hydrochloric acid. The 1.68 kilojoules is the amount of energy produced by a different amount. And why the acid and not the base? Because according to the question, the reaction proceeds until all the acid is used up. There is an excess amount of base, remember? So the energy released by the reaction is dependent upon the amount of acid, the limiting reactant, consumed. So the next thing we need to do is find out exactly how many moles of hydrochloric acid was consumed in the reaction to produce the 1.68 kilojoules of energy. We use the number of moles equals the concentration of the acid multiplied by its volume formula, and get 0.025 moles of acid consumed. So if 0.025 moles of acid produces 1.68 kilojoules of energy, how much energy is produced by the reaction of 1 mole of acid? We determine this by rejigging our enthalpy equation so that it's in terms of molar enthalpy. So 1 mole of acid produces 67.04 kilojoules of energy. Notice that the calculation used 1.676 kilojoules instead of 1.68. Rounded answers are just that, answers. Do not use rounded answers in any of your calculations. Now I've run out of space here, so I'm going to write the thermochemical equation on the next slide. If the molar coefficient of the acid was different, then the enthalpy change in the equation will be raised by a factor of that amount. That is, if the coefficient of the acid was a 2, then the enthalpy change will be multiplied by 2.